Hello everyone, I'm glad to be here in conference and represent my team to record this video. Our topic is metamorphic testing for network scanning. Here are my teammates. In this video, we are going to briefly introduce the background of network scanners and metamorphic testing, and how we implemented the metamorphic testing for network scanning. And finally, we will discuss the experiment's result. So, what is network scanner? Network scanner is a tool that's used for network detection. They play important roles in network information gathering, which is the third step in penetration testing. They can help both hackers and security auditors to detect hosts in the network environment. This figure shows the TCP three-way handshake process, which is the concept that used by scanner to detect hosts. The basic idea is the scanner sends a package to hosts, then analyze the response so it can recognize the target. Network scanning is a trade-off between speed and accuracy. Current network scanning can be classified as synchronous mode and asynchronous mode. Those scanners that adopt synchronous mode and send a request to the target host and wait for a response until timeout. The disadvantage of this type of scanner is slow performance. The scanner will not continue to the next target until the current connection is closed. The advantage is they are more accurate because they can identify the lost packets. Nmap is an example of this type of scanner. A synchronous mode scanner do not rely on the completion of the current connection to start the next one. They have separate transmit and receive threads, allowing high-speed scan. However, these scanners are less accurate because they cannot detect the lost packets. They usually have a threshold to limit the maximum number of threads, which will be closed if the packets sent do not reply on time, thus making space for new threads. However, this means that the scanner may miss information from the target hosts. Masscan and Nmap are two popular examples. In a project, we choose Nmap and Masscan as test targets. Nmap is a free and open source utility for network discovery and security auditing. It was designed to rapidly scan large networks but work also fine against a single host. It is flexible, powerful, and easy to use with well-documented and supported by a vibrant community. Nmap is a network port scanner with the ability to transmit up to 10 million packets per second through its asynchronous architecture. Compared to Nmap, Masscan has this port scanning function and only supports IP addresses and simple ranges. In traditional software testing, commonly, we generated test cases through a specific algorithm. Run these test cases against the system under test and check the results through a test oracle. The test oracle is a mechanism for checking whether the test cases can pass or not. It might be numbers, document, program, human, and may come from a specification, manual, or so on. If it is impossible or too expensive to use the test oracle, then this situation is called oracle problem. And the testing of the network scanner may be encountered because it is difficult and expensive to verify the scan results. The network environment changes all the time, and a scanner can give different results when scanning the same network segments within a short period of time. Using different scanners to check each other's results may be helpful, but there is still no guarantee that the results are correct. The reason is that there's an extreme assumption that all scanners participating in the test may encounter errors at the same time. Furthermore, Considering intrusion detection system and firewalls will filter certain data from scanning tools. Some scanners may have special scanning strategy to provide alternative options to meet different scanning requirements. This makes the comparison or verification more challenging and expensive, because it is difficult to find another appropriate scanner to compare with. Therefore, checking results of scanners face an oracle problem. Metamorphic Relations has been proven effective at alleviating the oracle problem. It checks the system under test with necessary properties among the multiple input and outputs. This kind of property is called metamorphic relation. In total, we identify 7 metamorphic relations for network scanners. Among these relations, 5 of them are for network discovery. 2 of them are for post-scan and service enumeration. We do not test the service enumeration because it took too long to run. So you will see 6 MR results in the later slides. Here's our test harness architecture. The test cases generator generates test cases according to a certain roles and delivers them for execution. Multi-thread pools allocate a main thread pool to process a bunch of cases and then create a sub-thread pool for each case to run its scan tasks at the same time. MR verification functions checks whether or not the collected data violate the relevant MR. Here are the test results for Nmap. MR1 checks the app hosts found by the task scanning segment AB is equal to the sum of the 2 separate tasks scanning segment A and B. The MR1 pass rate is only 55.28%, which is much lower than the other MRs. Although the time difference ratios of the failure cases in MR2 is much greater than that in MR1, it has a better pass rate, 84.3%. This suggests that the Nmap may be least accurate in large scan scanning. MR2 and MR3 are grouped together because they use the same set of tasks. MR2 checks that the task scanning more pools find as many or more app hosts as the other task. As previously mentioned, the time taken by MR2 in fail cases is much greater than average. However, even if taking the time difference into consideration, there appears to be several hosts that are not checking correctly. The pass rate of MR3 is lower than that for MR2 because it involves stricter requirements. MR4 checks if the 2 tasks with different scan sequences detect the same numbers of app hosts. The pass rate is 83.17%, and the value of number difference indicates a negative performance. Note that the timings and time difference in fail cases are more than double the average value. The reason is that OS detection may sometimes incur considerable running time, resulting in deviation. MR5 checks that the task in TCP sync mode, in TCP sync and ACK mode, find more app hosts than the TCP sync mode. This MR have very few violations with a 99.4 pass rate. The 3 violations are caused by network transmission errors or other unknown reasons, since the timings in fail cases is dramatically higher than average. It gives evidence that Nmap has stable functionalities in sync or ACK sync scan mode. MR6 checks that the operating system detected by 2 scans in different orders is the same. Although the pass rate is 98.11%, it was not confirmed whether or not the identified operating system was correct. This function basically just guesses the operating system. The source output of Nmap also provides the possibility of multiple potential operating systems. We took the most possible operating system as a result of Nmap. As discussed earlier, operating system detect can take a long time. For Masscan, it showed much lower accuracy on MR1 or MR2. In conclusion, we reported a study conducting metamorphic testing on network scanners. We found that Nmap has lower accuracy when scanning 2 segments than when scanning as 1 segment. But it appears to perform well when scanning multiple ports. It also appears to offer different stable scan modes. The time taken from Nmap to scan 2 segments was not simply twice that for scanning a single one. We also found that Masscan is fast but low accuracy. In the future, we also look forward to further examining some of the surprise results and observations from the study. Other scanners beyond Nmap and Masscan will also be studied in the future. Our hope is to be able to apply metamorphic testing to network scanners to resolve the possible software faults, but also to better enable comparison across different scanners. Thank you.
Okay, so let's start the question and answer session. And thank you very much for your excellent work. So we have the first question from our chat page. The question is: it seems that the performance was a relevant issue in this evaluation. So have you considered using MT for detecting performance bugs from
Yes. Okay. Thank you for your questions. Of course, I've considered to use the metamorphic testing for testing detecting the performance bugs. The key function of the network scanners is scanning the live hosts in the network. And in the paper, I come up for 7 metamorphic relations. Basically, idea is check the in the network and the service run on the hosts and seeking the relations between this output of the different tasks. Am I clear?
Okay, so Sergio, is this answer clear enough, or do you have any follow-up question with regard to your first question? Okay, so while we wait for other questions from the chat page, I have a question. So maybe I didn't completely understand your key points. So could you please explain in more details about the Oracle problem when you try to test the network scanner? So what exactly the output format is and why it is very difficult to verify the correctness? And could you please, I know that you mentioned about this in the first
internet connection.
Okay, so maybe wait for a while.
In the wrong way.
Okay, so where we'll stop. I see you mentioned about the Oracle problem in the introduction. Could you please explain a little bit more about why it is an Oracle problem?
Okay. Actually, I think the network scanners is similar with the search engine like Google, something like that. And the network environment is very complicated. For example, if we scan segments in the network environment several seconds ago, and it gives us 7 app hosts, but after several seconds, it can be 10 or less or more. So the environments change a lot, and we need to check in this moment the network scanners give us a correct answers is unstable. I mean, and in the other hand, we can the whole network environment is invisible. We cannot see them by our eyes. So what we can only depend on is the network scanner tools. But how we test it, because we don't have another way to prove it. So we can basically prove the result by use itself. I mean, so it's quite difficult to test the default of the network scanners.
Yes, I see you mentioned about here's a one sentence in the introduction that the network environment changes. You also mentioned just now, right? The environment changes all the time, and the scanner can give different results when scanning the same network segments. But so my question is, well, I mean, if you consider, do you mean that you try the same scanner and enter the with the same network segments but get different results? If you get these answers, do you consider it as an issue or consider it as just a normal phenomenon, because environment is just like what you said, is changing all the time? How do you consider this observation? Because you mentioned about it change all the time and the result change all the time, and how can you, what do you consider about this observation? Is it an issue or it just not?
It's not an issue. It's normal. So we need to solve it. We need to solve it when we're checking the output.
But do you have some similar phenomenon in your experiment? I mean, when you test the scanner and when you tried it several times and you also get different results, do you have this kind of? So how do you consider this? Did you consider it as violations because you observe different results? Since you observe different results, then how do you consider as? Yeah,
I got you. So the network environment will be changed is correct. So when I generated the tasks, I make them run at the same times and end at least similar in codes. And I mean, so in this same periods, the uphosts in the network environment is an exact. I mean, it's a certain numbers. It will be no change. But if the two tasks give us the different result, it can be considered a relevant. Error.
So in your experiment, so you can control the environment to make sure that the two outputs should be the same. Otherwise, it can be considered as a violation, right?
Yes.
Okay. Another question, because we still have some time. Another question, you mentioned about your table 2 mentioned about the time mean, time different, time mean in failed test cases. So why did you mention about these measures? Are these measures related to your MRs, related to the output of your MRs?
Yes, it's related because sometimes one test will run too long, and so there will be something like the network congestions or poor signal, something like that. It will make you stakes fail. So I need to feed out from when we analyze the data, and also we can I can compare the timing to see if the situation, the basic situation of this network. So
they're not directly related to operation.
Yeah. It's not directly, but
Some
it can
relevance.
give you some information. Yeah, it can give you some information.
Okay, I got you. So then, so when you get the result, how do you tell whether there's something wrong, or does it mean, for example, you have a very long time difference in failure test cases? I mean, is it better for a longer measure or a value or a shorter value? So how do you consider, how do you utilize these measures?
I would say it will average. If the test consumes in average, I will be consider it is a good test example.
Okay, so did you find any real life bugs in your test objects? Some real bugs? Did you find any in your experiment?
Sorry, could you repeat again?
I mean, did you find any real life bugs in your experiment?
Real life bugs.
I mean,
Okay,